Welcome to the Electronic Security Networking Technician webinar number 2, section 2 from Slayton Solutions. The Electronic Security Networking Technician Training and Certification Program is a complete and extensive training and testing program for physical security technicians and personnel, people who need to know how to properly install IP-enabled CCTV cameras, access control systems, door locks, intercoms, all of the devices in the physical security space. This program is administered by the ETA, the Electronic Technicians Association, who divides the program and the testing materials. This program consists of a 9-section webinar training, of which this is section 2, along with a 1-day hands-on networking lab and written certification test. If you would like to complete and receive, if you want to complete this training and receive the ESNT certification, you must complete the webinar sections and you must attend one of these live classes. You can check our website at www.slaytonsolutionsLTD.com for certification classes and testing dates in your geographic area. My name is Dave Ingebrigtsen. I'll be your instructor today. I've been in the electronic security industry for the last 33 years. I'm Network Plus certified, ESNT certified, fiber optic certified, and I run a company called Slayton Solutions. We provide a live and webinar-based training for the physical security industry. This section of the training deals with network addressing, and it's a really important section because it's the addressing we have to do properly when we install devices onto networks to get them to communicate. If we don't address them right, they're not going to work. So we need to look closely at how this addressing works, and that's what we're going to explain in this training session we're going to do right now. So let's get started right away, and let's talk about the couple of kinds of networks that you're going to run into in your customers' locations. Now, in a home or a small business, very often you'll see a network that's called a peer-to-peer network. This is where if you've used, say, Microsoft Windows Network Setup Wizard, and you use that on your network, you turn on all the computers on your network, they find each other, and then you set up where you can share files and share folders across the network. And these kind of networks work perfectly well. I have one in my own house. The thing to watch out for is that you've got to make sure that you centralize your important data storage and that data is backed up onto some kind of backup drive or some other mechanism, because I'm here to tell you that hard drives will fail, and they do fail. And if you keep your data in your computer and your wife keeps her stuff on her computer, well, one day one of those hard drives is going to die and you're going to lose that information. So what I do is I store everything that's of any importance on my wife's computer, which has a plug-in backup drive on it, which mirrors her hard drive. So I've got my data stored in 2 places pretty much simultaneously. So that's what you see in a peer-to-peer network. Now, in most of our enterprise situations, we're going to see the client-server network. Now, we're going to be talking about the addressing on this stuff. And what I want you to understand is that our client computers, the ones you see on the right side, the computers that are in the cubicles or on the desktops or the netbooks or laptops that are either wired or Wi-Fi into the network, those are typically going to get what we call a DHCP or a dynamic address. That means that when they're started up in the morning, the computer calls out to the network and there's going to be a device on the network. The computer is going to call out and say, hey, I need an address. Somebody give me an address. And there'll be a device on the network called a DHCP server, Dynamic Host Control Protocol server, that issues out dynamic addresses. You've got one of these in your house, I'm pretty sure, or your business, because they're built into Linksys, D-Link, and Belkin routers, and they're built into the router devices that are typically on our small networks, and then there are bigger DHCP servers and separate DHCP serving software that can be installed in separate servers in bigger networks, and it can get pretty complicated. But there's a DHCP server out there, so when the worker comes in and turns on his computer in the morning, his computer calls out to the network and says, hey, somebody give me an address. The DHCP server issues it an address. So these computers on the right-hand side, they get addresses and they don't really care what the address is because they're going to get the stuff they need. That would be the files, the applications, and the things that they need over the network. They're going to get it from the servers that are on the left-hand side. The servers are going to store the files, store the applications, and provide the users with the information and data they need to go about their work and their business. What's important to understand here is that our servers always have static IP addresses, and we've got this underlined here because that's an important thing to remember. Where the client computers can have a dynamic address and the address can change, our servers have static IP addresses. And they must have static IP addresses because the clients have to know, where do I call to get the information that, or the files or the applications that I need. Now, I want you to look at this drawing that's on the screen right here and think about, okay, we're going to put an NVR, a network video recorder, on our customer's network. Is it going to be a client or is it going to be a server? It's going to be a server because what does it do? It serves network video. It serves, surveillance video to authorized users. So our devices, and this is an important thing to remember, our devices, whether they're cameras, encoders, NVRs, access control panels, door locks, intercom panels, whatever they are, our physical security devices that are connected up to the network are servers, and they need static IP addresses to function properly. They can't really work well with dynamic addressing. So that's an important thing I want you to remember. Right now we're going to get into a little detail about how addressing gets put together in the data packets. This is some important stuff because we need to have an idea of what's going on in this OSI protocol stack and what's going on in the TCP/IP stack. We've got all these addresses. We've got MAC addresses. We've got IP addresses. How does this all fit together? Well, we're going to try to explain that to you right now. What you're seeing here is a example of encapsulation where we start at the top with that applications data, and as the data moves down through the protocol stack, additional layers, or additional address headers are added to the packet. They make the packet longer, but they address it in a particular way so that when the packet's transmitted, the receiving computer knows what to do with it and where it's supposed to go, what kind of application it is, what kind of protocol it is, that sort of thing. So as the data moves down through the protocol stack and gets like let's say it's going through the stack on the right-hand side, as it comes down through the protocol stack, it gathers this address header information, and then that is transmitted in bits out the physical layer, and then it comes over to the stack on the left-hand side where it comes in on the physical layer, and then the packet moves up the protocol stack, and as it moves up, those addresses are checked and discarded. They're stripped off, and we end up at the top with the application and the data that is associated with it. One of the things you need to understand about networking is a concept called encapsulation. It's illustrated on the screen here. Let's talk about it. This is the process where really we've got three basic types of addresses that all come together to make a single data frame, Ethernet frame. That's there at the bottom. So let's talk about what those address types are and a little bit about what they do. We're going to get into them in more detail as we go along. We start at the top with something called the segment. Now in the segment, we've got the data over there on the right-hand side, and we can't forget about the data. That's the video, the voice, or the text. That's the meat in the sandwich. That's the important stuff, right? But we've got all this addressing we've got to put together. The first type of address that's up here in the segment, which is also layer 4, or the transport layer, is the source port and the destination port. Now, you can think about I call them software ports. You can think about these software ports kind of like cable TV coming into your house. You've got a cable TV service coming in. You've got one piece of coax coming into your house, and on that, and you've got 300 channels on your TV set, right? Or 200 or whatever you got. You got a whole mess of channels. Well, just as your cable TV service has a whole lot of channels coming on one piece of copper, you've got one internet connection, but your one, like a typical house like mine, I got a DSL adapter. You have one internet connection coming in, and in TCP/IP communications, we've got channels. They're called software ports, and there's 65,535 of them. So you got lots of channels. And we're going to talk about how we manipulate those channels, those software ports later to set up network address translation so that we can view an IP camera. We can call into an NVR that's on a network. We can call devices up over the internet with our iPhones or with our laptops or with whatever device we've got that's on the internet. But that's something we're going to get into. But right now I want you to look at this encapsulation, think about the segment. We get a source port and a destination port. What port is it going to? What port is it coming from? That segment drops down into a thing we call the packet. Now this is layer 3. And in layer 3, this is where our IP addresses get put on, our Internet Protocol addresses. And we have a source and destination IP address. We also get a thing called the protocol, and we're going to talk about those protocols later, the common protocols that are used. I consider them sub-protocols within the Ethernet structure. But we'll talk about those a little later, TCP and UDP. And then everything from the segment falls down into the packet. Then everything from the packet falls down to layer 2, which is the data link layer, and this is where the MAC addresses, or media access control addresses, get put on. There's a destination and a source MAC address. These are the addresses that are used for communication through the local network. They are the Ethernet addresses. They're also called the physical address. They're also called the MAC address. So those addresses are put on. Everything from the segment and the packet falls into this frame, Ethernet frame, and then at the end we have the frame check. And the frame check's important because it's a checksum, so that if I'm a transmitting computer and you're a receiving computer and I transmit to you a packet that's 146 bytes long, as you are receiving the bytes of data, you are counting them. And so you get to the end of the count, and then I send you the frame check that comes at the end of the packet that says this packet was 146 bytes long. Now, if you counted 146 bytes and the frame check is 146, then you know that the packet is true and accurate. If, however, you counted 142 and the frame check came as 146, then you would know the packet's defective. So do you see that at the packet layer or the frame layer itself, we Ethernet checks to verify the validity of the data that's been transmitted. So this frame check is very important. So here you see what happens in layer 2, our data link layer. This is where we have our Ethernet frame. This is what it looks like. We've got and it's going from the right to the left. So we've got our destination address. That's our destination MAC address, our source MAC address. We're also going to get the IP packet information. We're also going to get some data that tells us that this is packet number 23 of a total of 172 packets. There's going to be a packet number, so that if the receiver gets a bad packet and has to call back to the transmitter to get that packet replaced, it can tell them which packet it is. Hey, you know, the one I got that was bad was number 123. Okay, fine, I'll send you a new number 123. This slide also illustrates the point that our Ethernet frames can be longer or shorter. They can be as short as 64 bytes of data. They can be as long as 1,518 bytes. So an Ethernet frame can be longer and shorter. Now let me point out one thing back on this encapsulation that I kind of skipped over. Understand that this encapsulation is important because not all data that's transmitted through all the networks we're connecting up to is in Ethernet. So let's take the example of what I've got on my desk. I've got my computer, I've got my router, I've got my DSL adapter. The connection between my DSL adapter and my router is what? It's Ethernet. It's an RJ45 socket that plugs in to my router and plugs into my DSL adapter. So if I'm on my computer and I want to go to ESPN.com to look at the football scores, those packets are going to reach my DSL adapter and they'll be Ethernet frames. But is the communication protocol between the DSL adapter and the internet service provider, in this case SBC or AT&T now, is that in Ethernet? No, it isn't. It's in a different protocol. It's in a protocol typically called, the typical protocol used in DSL is called ATM, or asynchronous transfer mode. So what does that make our DSL adapter? It makes it a translator. Your packets, you're sitting there saying, I want to go to ESPN.com. Those come to the DSL adapter as Ethernet. The DSL adapter converts them, re-encapsulates them into Ethernet frames, and transmits them up to the Internet service provider. The packets that come back from ESPN.com are going to be in ATM. Your DSL adapter is going to translate them back and re-encapsulate them back into Ethernet so that they can be seen and viewed by your computer and transmitted through your Ethernet network. So that's why this encapsulation issue is something that you need to understand. Now, when we talk about device addressing, let's just review where this fits in terms of our IP protocol stack and our OSI model. Our layer 4, our transport layer, this is where our software ports get designated. Our layer 3, our network layer, this is where our IP addresses are. Our layer 2 is where our MAC addresses are. And the bits that are the ones and zeros go out on the physical layer. Now notice in red over here, on the left-hand side, we talk about some devices that fit at certain places in these protocol stacks. And our NIC, or network interface card, that's built into our PC or built into an IP camera or NVR, that NIC is going to be on layer 2, which is your data link layer. Then we have our router, it's layer 3. The router reads IP addresses. Our NIC is at layer 2, and our network switches are at layer 2. Network switches, we're going to talk about them in detail, but network switches read MAC addresses because they work on the local network. The router reads the IP address so that a packet that is destined for another network, like the internet, the router reads the IP address of that packet and then transmits the packet to where it's supposed to go to try to complete the communications that are being attempted. So now we've got 2 levels of addressing that are in every data packet that's transmitted. We've got both the MAC address and we've got the IP address. What I've got here is a screenshot from a software called Ethereal, or now it's called Wireshark. And what Wireshark does is it's a protocol analyzer. It tells you what it gathers the packets that your computer sees and gives you all the details about it. And this is a screenshot from that, and it just shows you that when a data packet is transmitted, this one was 260 bytes long, that it has the destination MAC and the destination IP address. It also has the source MAC and the source IP address. So every data packet is going to have those MAC addresses and those IP addresses on them. Now, the MAC address is really pretty simple to understand, or I should say it's simple to work with, because they're set at the factory. We don't set them in the field as installers. MAC address is also called Media Access Control Address, also the physical and Ethernet address. It's 6 groups of 8 bits, so it's going to be an address that looks like this. Here you see what is circled when I did an ipconfig /all to my computer, and my MAC address comes up as 0006252877F7E. And notice it says it's a Linksys Instant Wireless card, because whether it's wired or wireless, if it's Wi-Fi or Ethernet, we've got MAC addresses. Remember that now. Now, the MAC addresses are put on at the factory when a manufacturer makes products. Let's say I decide that I want to start making IP cameras in my basement. I would contact an organization called the IANA, or the Internet Assigned Numbers Authority, and I'd say, I'm Dave, I want to make cameras in my basement, and I need MAC addresses. And what they're going to give me is the first 3 groups, which you see, or the first 24 bits. This is going to be a manufacturer identity listing. So how does when I did ipconfig space/all, how does my computer know that it's a Linksys Instant Wireless card? Because the first three groups here, the 00, 06, and 25, is going to be the same for every Linksys wireless card that's made. The first three groups stay the same. The last three groups are a serial number for the particular device. And what this means is that MAC addresses are supposed to be unique. And when I say unique, we'll talk about, we're going to use this word a lot in this training program. There's nothing else in the world like it. Just like you're a unique human being, you know, you might meet a guy that's got your same first name. I meet guys named Dave all the time. But we're different. We're different Daves. I've got a different last name and I've got a different social security number, right? So even though we're both Dave, we're different Daves. MAC addresses are supposed to be unique in the world. No device is supposed to have a duplicated MAC address, okay? And understand this, it's important to know that the MAC address is what's used to communicate. It's used to address the packets on the local network, on the LAN, and it's a layer 2. Remember that, MAC address is layer 2. It's the data link layer. And again, here you see the graphic that shows us how we can gather the MAC address of a PC if we're sitting at it by doing ipconfig space/all. Now, so we've got all these manufacturers building all this network equipment, and every one of them is putting MAC addresses into their devices. So how are we going to logically separate our network devices? Because you don't want your neighbor getting into your network and looking at your devices, and you don't want to look at your neighbor's devices. So we have to create what I call, think about a gated community. What makes a gated community? Well, it's got a fence around it or some physical structure, and there's a fence around the gated community, and inside the gated community are the houses and the golf course and the pool. And then at the front of the gated community, there's what? There's the gate that lets people in and out. There might be a guard there, or it might be a card access sort of situation. Well, we need to build gated communities for our networks of devices. And these gated communities, we set them up by putting in the IP addressing. And it's the IP address that we must be able to do accurately to put into the device. Remember, you can think about IP addresses like the license plate on your car. I've got a Jeep Liberty. On my Jeep Liberty, in front of the steering wheel, there's a little metal plate that's got my vehicle identification number or my VIN number. There's no other Jeep Liberty in the world that's got that VIN number, right? It's a unique number for my Jeep. Now, on the back of my car, there's a license plate. I live in Illinois, so I've got an Illinois license plate. If I decide to move to, I don't know, Ohio, and if I take my Jeep there, at some point I'm going to take off my Illinois plate, and I'm going to register my vehicle in Ohio, and I'm going to get Ohio plates, right? So do you see that I went from the Illinois network to the Ohio network, and my VIN number stays the same? This is the same thing with the IP addresses. We are doing what's called logical addressing, and we're separating out our devices to say these devices can talk to each other because they've got the same addressing scheme and the same addressing setup. And it's the IP addresses, ladies and gentlemen, that you must be able to set properly. That's one of the 4 things you must be able to set properly in any device you want to connect up to your customer's network. But they are settable. We're going to show you how to do it. But first, let's talk about what these IP addresses are about. The most common way devices are addressed on local networks is called IPv4. IPv4 consists of 4 groups of numbers that are separated by periods, and each of these groups of numbers is called an octet. It's a decimal representation of a binary code. So here you see what an octet looks like. There are 8 positions from 128 to 1, and remember that everything in networking is transmitted as 1s and 0s. So we can either turn on a position by transmitting a 1, or we can have the position turned off by transmitting a 0. So in the example you see on the screen, we turn on 128, we turn on 8, we turn on 2, and if we add those numbers together, we get 138. So what we call, and we commonly call, an IP address is actually a decimal representation of the binary code. How could we write 192? We could write 192 by turning on the first 2 bits here, 128 and 64. So we could write 192 as 1, 1, and then 6 zeros. That could be our IP address, but that would be difficult to deal with, and most people, binary is a bit of a challenge. So to make it easy, we have a decimal representation. So what does this mean here? This means that in IPv4, these octet positions that are separated by periods, the valid numbers in them are going to be from what? Well, if all these are set, if all the bits are set to 0, it's going to, the lowest value can be 0. What can the highest possible value be if every bit is turned on? If every bit's turned on, the highest value is 255. Therefore, in each of these octet positions, the highest value is 255. The lowest value is 0. If you put a number in one of these octets that's higher than 255, it's not going to work. Now, one of the things I want you to understand is that every PC on a local network has got a local IP address, and if it's hooked up to the internet, it's going to have a public IP address. Let's take a look at my computer right now, and we'll look at how this works. We can go to Run, and we can type CMD, and we are going to get our command line, and I can say ipconfig. This tells me the IP address of the PC itself that I just did it to. So it's telling me that my IP address, or my local area connection address, my LAN address, is 192.168.1.102. It also gives me my subnet mask and default gateway. Those are things we're going to get into a little bit later. This tells us what our local address is. Now, if I want to know what my public IP address is, I can go to Internet Explorer, and I can type in, once my Internet Explorer wakes up, I can go to Internet Explorer, and in the address line, I can type in, ask me later. I can type in www.whatismyip.com, and it's going to come up and tell me what my public IP address is. So, every device on a local network, and here you'll see what my public IP address, right now it's 99.140.175.163. I get a dynamic public IP address, and we'll talk about that later, because there's just as there are static and dynamic addresses in local networks, there's static and dynamic addresses in the internet. So every computer or IP camera or DVR or whatever it is, that's everything hooked up to the local network, is going to have a local address. And that local address must be unique, ladies and gentlemen. One of the biggest mistakes you can make in networking is to duplicate a local IP address. So you can think of the local IP address like the street you live on and the number of your house. I live at 1515 Main Street. My friend Tom lives at 1520 Main Street. So we're both on Main Street. He's a couple houses down from me. I'm at 1515. He's at 1520. And just as the houses on your street, the properties must have a unique address. You can't have two houses with the same address, right? Every device on the local network must have a unique local address, okay? Now, I tell you I live at 1515 Main Street. You say, well, that's great, Dave, but there's a lot of Main Streets in this great country of ours. Which one is it? Well, if I say I live at 1515 Main Street, Chicago, Illinois, 60622, well, now you can pull out a postal map of zip codes, and you can say, oh, yeah, he lives in Chicago. That's where he lives in Chicago, right? So that's like the public IP address. And understand that if Tom lives 3 houses down from me at 1520, he's got the same zip code, city, and state. So you can think of the public IP address as the zip code, city, and state, the local IP address as the street number of the house, on the street. Another example, this is Dave's accounting company, and we've got 20 accountants hooked up to our network. And we've got one DSL adapter that provides internet connectivity for all those PCs, right? They'll each have a unique local IP address. It could be static or dynamic. But if you IP config each computer is going to come up with a different local address. But if you did the whatismyip.com trick on Internet Explorer, it comes up with the same public address because they're all going through the same DSL adapter. So every device on a local network must have a local address. If the devices are connected to the Internet, there is also a public IP address. These addresses are layer 3. These are the addresses that routers work with. And these are the addresses that we must set properly in the devices that we're programming onto our customers' networks. So we've talked about the octets, and now here you see when we do ipconfig /all, not only do we get the MAC address we talked about above, but we also get the IP address, and in this case, that's what's circled is the subnet mask that we're going to talk about here in just a few minutes, which is another piece of the address puzzle that we have to fill in when we're programming a device to put it onto a local network. Now, how do we get from the MAC addresses to the IP addresses? So it's a real interesting technique that's used. If I'm sitting, this is another screenshot from Wireshark. And what we've got is a source and destination IP addresses. We've got a protocol, and we've got information. So our source over here on the left-hand side, the one that's in the gray box, 192.168.1.101. That's my desktop computer. And I want to go to one of the cameras on my network. Now, when I go to Internet Explorer and I type in an address, I don't type in a MAC address, do I? No. I type in an IP address. I say I want to go to 192.168.1.10. How does my computer that I'm sitting at, how does it find the MAC address of that device? Here's what it does. It sends out a broadcast packet. And a broadcast packet is one where the MAC address is all Fs, it's all Franks, and the IP address is going to end in 255. That's what's going to be in the last octet in a typical Class C network. And it's going to transmit an address resolution protocol, or ARP, and it's going to say, who has the IP address 192.168.1.10? Please tell 192.168.1.101. Now, look at the second line. Here you see the camera, it happens to be a camera, calling back directly to, it's at 192.168.1.10. It's calling directly back to my PC, 192.168.1.101, in address resolution protocol, and it says, I got that IP address, 192.168.1.10, and my MAC address is what you see there, the 6 groups of letters and numbers that are 0 through 9 and A through F. Here's my MAC address. Now my PC has got the MAC address of the camera, and now my PC will start to address the packets to it. And this is how we resolve from the MAC address, or from the IP address, to the MAC address. So this is how the two of them link together. And this is the way it's done. It doesn't matter what kind of device it is. If you're sitting at your computer and you want to go to the server on your network and you type in the address into your computer, you type in the IP address, your computer's going to do this broadcast. And the devices that it can hit when it does this, all those devices put together is what we call the broadcast domain. Now, we have to think about the broadcast domain when we're designing networks. If we're, IT people, and we think about these broadcast domains, because the more devices that are on the network, let me explain it this way. When I called that camera and I wanted to see the pictures from the camera, my computer did the broadcast. It gathered the MAC address. It registered that in something that's called the ARP, or Address Resolution Protocol file table. It holds that address as long as that communication session is in process. So let's say I call the camera at 10 o'clock in the morning, and I look at the pictures for a few minutes, and then I turn off that camera feed. I don't want to look at it right now. And then 10 minutes later I say, I want to look at the camera again. When I call the camera back 10 minutes later, guess what? It goes through the whole process again. So do you see that the more devices we have on a network, the more broadcasts are going to happen. And broadcasts slow down network performance, because when a broadcast happens, every device must open the packet. When this client computer over here on the right-hand side wants to talk to server 192.168.10.15, it sends out the broadcast packet. Those broadcast packets go to every device on the network. So every device has got to stop and open the packet because it might be for them. The only one that responds is 192.168.10.15, but we slowed our network down a little bit when we did that broadcast. This is one of the reasons that, let's go back to the IP addresses for a second. We're going to talk about Class A, B, and C, and D addresses here in just a few minutes. But what I want you to understand is that even though we can have up to 254 addressed devices on what we call a Class C network, very rarely do they build a network with that many devices on it. Because if we've got 254 devices that are all sending out broadcasts all the time, our network's going to run pretty slowly. So this is one of the reasons that they'll limit the number of devices on a particular local network, because of this broadcast domain issue. Now, this brings us to how IP addresses are set up. And the way they're set up, when they originally conceived of this concept, they set up what are called classes of IP addresses in IPv4. So we have Class A, Class B, Class C, and Class D. There actually is a Class E, which is an experimental addresses. We don't have to concern ourselves with them. What's a Class A network? A Class A network is where the first group stays the same, and then the last 3 octets are variable. That makes a huge network. A Class B network is for a smaller but still very large network, where the first 2 groups stay the same and the last 2 octets are variable. Class C networks. This is the most important one to us, because this is the kind of local network that we're going to need to connect our devices to. And in most cases, the Class C network, the networks our customers use, will be Class C. And a Class C network, the first 3 groups stay the same. The last octet is the only variable. So what does this mean to us? It's real important for you to understand that when you go to a customer's location and you're going to connect up an NVR or camera, you have to know what their addressing scheme is on their network. And you must, if it is a Class C network, you must match the first 3 groups exactly. If the customer's network is 192.168.1.something and your NVR is programmed 192.168.3.something, it won't work on that network. It will not communicate. It cannot communicate. So this is important to remember. When you are working with Class C networks, and these are the types of networks you're going to work with 95% of the time in the local, hooking things up to the local network, those first 3 groups must match. The last group is variable. That means that, as you will see in our Class C networks, we can have up to 254 separately addressed devices. Class D addresses are multicast addresses, and we are going to address multicasting in a later section of this training. So, along with these IP address classes, they set up ranges for the first octet. This is from the IANA, Internet Assigned Numbers Authority. They said, we're going to make the Class A networks where their first octet will be from 1 to 126. The number of networks, you see, I'm not going to read you everything on the screen, but you see that you can have 126 networks, and you can have 16 million plus computers or devices on a single Class A network. Class B, starts at 128. Class C starts at 192. You might have asked yourself, why is it when I buy a router or I buy a camera at a distributor and I pull it out and it's got a default address, and the default address, the first group of that IPv4 address is 192. Where's the 192 come from? Here's where it comes from. Because they set that up as the range for Class C addresses. They start with 192. You can have there can be up to 2 million, and obviously there's way more than 2 million local networks out there, and the number of devices per network is 254 individually addressed devices, because the zero address, 192.168.1.0, the zero address is going to be the network address, and 192.168.1.255 will be the broadcast address. Remember those broadcast packets. So that narrows slightly the number of individual addressed devices we can have on our network to 254. And you see the Class D addresses are up there as well. Now, along with these classes and they set up what are called IP address ranges for private IP addresses. Private IP addresses, this would be for a private network or a local network. The reason for the private IP addresses is that packets in your local network should stay in your local network. They shouldn't be out on the internet. If the internet routers see packets that have any addressing like you see here illustrated, 10.0.0 or 192.168, then the routers on the internet know these are local packets. They shouldn't be out here playing with the big boys, and so they'll kill the packets. Okay, so why does this concern us? Because this is where we get that 192.168. This is where 9 times out of 10, this is what people use for their local network. Now, let's push back for a minute and let's just consider something. In my house, I've got a network that is 192.168.1, and then I've got 8 or 10 cameras and devices hooked up to it. So I've got a Class C network that's 192.168.1. Now, my neighbor right next door can also be using 192.168.1 because their network is physically and logically separate from mine. I can't talk to their devices, they can't talk to my devices because they're not wired together, right? Or we're not on the same Wi-Fi access point. I certainly hope not that we're not. So, do you see that we can be reusing these Class C addresses? It's very common if you walked into 3 houses and you checked their networks, 3 houses in a row, that they'd all be 192.168.1. And that's commonly done. Now, over on the right-hand side, you see what are called the default subnet masks. We're going to talk about the subnet masks here in just a minute. In fact, we're going to talk about them now. What subnet masks do is this is part of the addressing. Remember that when we have an address that looks like this, let's look at this one where it says it's 172.16.0.0, and it's got the Class B subnet mask of 255.255.0.0. In an IPv4 address, or an IPv6 address for that matter, that one address line, that IP address, it has 2 elements to it. There's a network address and there's an individual machine address. So in this example we see here, we've got a network range from 172.16.0.1 to 172.16.255.254. Our broadcast address, 172.16.255.255, and a host on the network, just a random host address could be 172.16.3.18. But here's the point. Where you see the 255s in the subnet mask, the subnet mask is programmed into the data frames that are transmitted out. And it tells the receiver the IP address you're getting, the first 2 groups are the network address, the last 2 groups where the zeros are, the last 2 groups are individual device addresses. So the subnet mask is part of what I call the 4 magic keys. The 4 things that you have to program into every device that you're going to put on a local network. Those 4 magic keys are the IP address, the subnet mask, the default gateway, and the port numbers. And we're going to get to the default gateway and port numbers as we move along. But here you see our Class C subnet mask. This is the one you're going to use 99% of the, well, 96% of the time. 255, 255, 255, 0. That means network, 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 and the 0, the last octet, is going to be for individually addressed devices. So this is what you're going to use most of the time. Now, let me point one thing out to you. There are no IT managers can set up their networks any way they want. I've often gone into places to do training classes and said, well, I need to connect up to your internet. Oh, no problem. Just plug in. And I plug in and I set my computer for DHCP to get a dynamic address issued to it. And then when I check that address, I see that the address I've got is 10.0.0.23. So it's a Class A private address. But the subnet mask is 255.255.255.0. So what does this mean? They're using a Class A address with a Class C subnet mask. That makes this particular network a Class C network. It is the subnet mask that's used that defines whether it's a Class A, Class B, or Class C network. It's the subnet mask. So individual IT people can set up their addressing scheme the way they want to, but it's that subnet mask that determines whether it's Class A, Class B, or Class C. Now, we're going to talk about subnet masking and how we can manipulate in a Class C network for this example. In a Class C network, we can manipulate the last octet so it doesn't end in 0. So it ends with a different number. And what does this do when we do subnetting or subnet masking? What we're doing is we are going to take our Class C network, and in this example, where we're doing 255.255.255.192, we're going to take that network that can have 254 addresses, and we're going to divide it into 4 subsections or 4 subnets. So when we put that .192 on the end of the subnet mask, this is what we're doing, because we're setting the 2 bits, the 2 first bits in that last octet. They can be set one of 4 ways, as you see listed on the bottom of the screen. They're either both zeros, 0, 1, 1, 0, or 1, 1. And these are the numbers that would be represented, 0, 64, 128, and 192. So what does this give us? This gives us 4 subnetworks that are grouped in this number configuration. And you see it all on the screen here, where we've got the network address, we've got the range of addresses, and we've got the broadcast addresses. Let's look at the group from 64 to 127. The network is going to be 192.168.1.64. Then our range of addresses is going to be from 192.168.1 from 65 to 126. And our broadcast address will be 127. Now what's important to understand here is that the host that is programmed, and when we say host, we're talking computer, camera, NVR, whatever it is. A host is an addressed device on the network. The host that's addressed, the address in the last octet is going to determine which of these groups it falls into. And then once it's programmed that way with this subnet mask, then it will only talk and communicate to devices within its own subnet group and will ignore communications from outside the group. So let's look at an example here. We've got, I call this the pie or the wheel of IP addresses, and it reads like a clock. We've got a network here that is 192.168.2 dot something, and our IP addresses start at the top at 12 o'clock, starts at 0, goes around like the hands of a clock, and comes to 255. Now, excuse me, let's take an example where we're going to take an IP camera and we're going to give it the IP address 192.168.2.80 with the subnet mask of 255.255.255.192. Now, do you see that puts that camera into the second quadrant, reading like a clock, the quadrant that is from 64 to 127. So now, when that camera is programmed in that manner, the camera will only communicate to devices that their IP address ends between 64 and 127, which is going to be the network address, the broadcast address, but anything that wants to talk to that camera must be in that group. So what this means to us in the real world is this isn't a problem, except the security director, the boss, whoever is supposed to be able to call into that camera must have an IP address, static or dynamic, that falls into this piece of the pie. Otherwise, they can't see the camera. The camera won't talk to them. The camera will not talk to a device whose IP address is 192.168.2.20. It'll simply ignore it. So here is what you need to remember. When you are working at the enterprise level, let's say you're going to put 15 cameras on your customer's network. You're going to go to the IT person. If you are connecting to the shared network, you're going to go to the IT person and say, I need 15 sets of magic keys. I need IP addresses, subnet masks, default gateways, and port numbers for these 15 cameras. So I can program them up and hook them up to your network. Normally, the IT person is going to give you a subnet mask that ends in 0. And when they do, that's perfect. That's great. Because that anything in the network can then, any other device in the network, that local network can then communicate to that camera. But if they give you a subnet mask that doesn't end in 0, this is what they're doing, what you see on the screen. They are going to limit what devices can talk to each other on their local network. Now, this subnet masking can be very complicated, and it's kind of a hard concept to grasp. Understand that subnet masking is an old school way to divide up networks. This is back before the development and deployment of what we call the VLAN or virtual LAN. Nowadays, IT personnel can separate devices and groups of devices on their networks quickly and easily using VLAN technology, which we're going to describe in detail in a later portion of this training. This subnet masking thing we're talking about is really kind of old school, but you need to understand if they give you a subnet mask for your device that doesn't end in 0, this is what they're doing, and you need to be prepared here and say, well, okay, that's fine. I can put that subnet mask in, but that means that the security director or the network attached storage that the camera is going to be sending its video to, or whatever needs to communicate with the camera or device that you're installing, be it an access panel, intercom, whatever it is, must fall into that group. Now, let's just take a look here so that you understand. Let's take a look at my router right now, and I want to show you that what subnet masks are available. So we're going to call it my router. .1.1. Bingo. And we say OK. And now notice here, in network setup, we've got our local IP address 192.168.1.1. And then if I click here, it shows me these are the valid subnet masks in a Class C network. They go 128, 192 in the last octet, 224, 240, 248, and 252. So I can separate my network. I can split it in half, quarters, eighths, sixteenths, 30-seconds, 64ths, and 128ths. Okay? So that's what subnet masking is about. And just remember, normally they're going to give you a subnet mask that ends in 0, and when they do, everything's cool. Now, another way to express the subnet mask is what's called CIDR, or classless interdomain routing. All this does is it takes the bits that make up the subnet mask and expresses them as a slash and a number to say, okay, our example with a 192.168.17.52/26, our network address is 192.168.17.0, and this is going to give us that first group of that 192 octet because we're using the first 2 bits of the subnet of the last octet. So it's just another way to express the subnet, but normally we don't use this in the devices we program. The devices we program, you're going to go in and type in the full subnet mask, in this case 255.255.255.192. So now we've got our subnet mask handled. We need to talk a little bit about IP addressing. There's 2 ways that IP addresses are put into devices. Those IP addresses can be either static or dynamic. A static IP address is just that. The IP address is put into the device, and it's always going to have that IP address unless somebody goes in and changes it. And these are going to be your servers. Your servers will have static IP addresses. Dynamic IP addresses are issued by a DHCP server. You turn on your computer, it asks, hey, somebody give me an address. And the DHCP server gives the computer, the PC, an address. Networks will have, if they are hooked up to the internet and have a router, they will have dynamic and static addresses at the same time. We can have dynamic and static on the same network at the same time. Now, first of all, what's the value of dynamic addressing? The value of dynamic addressing is that uninitiated users don't have to know how to put their IP address into their computer. The network does it for them. Okay? I could ask somebody, you could ask somebody, hey, you've got a computer at home, right? Yeah. What is the local address? What is your local IPv4 address? And the person would say, I don't know. And then you could say, well, what is your internet address? Your public IP address? I don't know. Does your computer work on the network? Oh, yeah. Can you go to the internet? Oh, yeah. That's the beauty of dynamic addressing. Our users don't have to know how to put in the IP, because not when your computer asks for a dynamic address, it not only gets the IP address, it also gets the subnet mask, it also gets the default gateway. So 3 of those 4 magic keys get covered by this dynamic addressing. But now understand that our devices, and I emphasize this again, our devices, our NVRs, our cameras, our video encoders, our physical security devices need static IP addresses. They are servers. You need to remember that when you're talking to the IT people, because you're going to say, I need 15 static addresses for these 15 cameras, and the guy's going to say, why do you need static IP addresses? The IT person wants the things to be dynamically addressed. Why? Because he's got control of the DHCP server, and he can go to that server and he can ask it, how many addresses have you got out there right now? And the DHCP server will tell it. So later on when we go into the router, I will show you that even a simple $50 router has got a DHCP table. It tells you what addresses are issued. Now, what's important here is that we don't use, when we are issuing static addresses for devices, like we're going to put 10 cameras on the network. That's great. As long as the static addresses we're going to put in the cameras do not fall into the same range as the dynamic addresses that are issued by the DHCP server. So, if we go to Internet Explorer again, and let's see, I still got my router up here. There it is. Okay. Down here you see the DHCP server, and it says DHCP servers enabled. You see the starting IP address is 192.168.1.100. Maximum number of users is 9. So what does this mean? It's going to issue addresses 1.100, 101, 102, 103, 104, 105, 106, 107, 108. That's 9 addresses, right? Those are the 9 addresses it'll issue. if I'm going to connect up a camera, DVR, NVR to this system, I want to make sure that I don't give it one of those addresses, that I give it an address that's outside of, that's a Class C address, so it's going to be 192.168.1. It says so right here, and that in the last octet, I'm not duplicating one of the addresses that can be issued by the DHCP server. Okay, so I'm going to pick I'm going to put an NVR on this network. I'm going to pick 192.168.1.150 or 225 or 20, something that doesn't fall in the DHCP server range. And I'll make this point here. There is no advantage or value to a lower or higher number in that last octet position. An address that's 192.168.1.20 is just as good as an address that's 192.168.1.200. It's not better to have a high number or better to have a lower number. It doesn't matter, okay, as long as the addresses aren't duplicated. Now, we can go to, I got to move this so I can show you. We can go to the administration of this device. I think it's in here. Let's take a look. Excuse me. I can go to my log, and I should be able to see, where is it in the status? I think it's in status here. DHCP local network here. Here's my DHCP client table. And so here you'll see these are the devices that have DHCP addresses right now. I've got a couple of Honeywell cameras. These are an exception to the rule that our devices need static addresses. The Honeywell Direct Connect system uses dynamic addressing, which is fine. It operates a little bit differently. But here you see Dave Desktop, Office Desktop. These are the devices that are on my computer right now. So even my inexpensive $50 Linksys router/switch has got this DHCP status information and gives us the a table that tells us, you know, and this is why the IT people like the dynamic addressing, because they can go to the DHCP server and say, who's got addresses right now? And it'll tell them, okay? And that's why they generally don't like to issue static addresses. But remember, we need static addresses for our devices. Now, there's another way that IP addressing is going to start happening. And the reason for it is that we're actually running out of IPv4 addresses because of the millions and millions of devices that are going on the internet now. Your iPhones, your cars, all these devices, laptops all around the world, computers, everybody wants public IP addresses. So they needed to develop a new method of addressing so they would have more addresses. So we have what's called IPv6. In IPv6, it's a 128-bit address that's got 8 sets of letters and numbers, A through F and 0 through 9, divided by colons. So what you see at the bottom of the screen would be a typical IPv6 address. Okay? So, and you can imagine that this gives us a whole lot more addresses than we had with IPv4, which is only 4 groups and is limited to numbers only, and it's limited by the number of bits in the address. Now, the good news is this. We're going to continue to use IPv4, I believe, for a long, long time in the local network. And IPv4 to IPv6 conversion, they're compatible with each other. So you see the example where the IPv4 address is 11.14.17.23. In IPv6, it's 2 colons, and then we use colons instead of periods between those octet groups. We're going to probably continue to use IPv4 in the local network. Eventually, sooner or later, you're going to start to see IPv6 addressing in public IP addresses, on those internet IP addresses. Now, it's going to be interesting because one of the things that they didn't think about, or maybe they thought about but didn't think it was going to be a big deal, there's been a very slow conversion to IPv6, and the reason for this is pretty simple. Let's look at the length of that address is 128 bits long. So now remember that each data packet must have its destination and source IP address, right? So suddenly the data packets got bigger because the address lines got bigger. If the data packets get bigger, they move through the network slower. So there's kind of an unintended consequence here. The addresses got bigger, so this is one of the reasons that the conversion or the acceptance of IPv6 has been kind of slow. The federal government mandates it for their networks, but in the private realm, we're going to be with IPv4 for a long time. So we don't, you need to be aware of what IPv6 is, but I don't think we're going to be dealing with it actively for at least a few years on the local network part of our connections. Now, we talked earlier about the software ports. They're like channels on a TV set. We've got port numbers from 0 to 65,535. Now, when we set up what's called port forwarding, we are going to program into a device, say it's an IP camera. We're going to set the port in that camera. Let's say the camera is going to communicate on port 8180. We're going to set up the IP address, the port number in the device, and then in our router we're going to do what's called port forwarding, so that if something comes from outside the network, tries to get through the firewall and through the router, we've got a user out there who wants to call into his NVR, which is at his office, and he's at home. Well, he's coming from the outside. Our firewalls and our routers are going to be default programmed to stop that outside traffic from coming into the network. Firewalls and routers, they're just like the doors on your house. You have doors on your house to keep the bad guys out and the good guys in, right? Or you've got a fence, like I live in downtown Chicago. I got a fence around my house and I got a gate, right? Keep the bad guys out and the good guys in. That's what that's what firewalls do, and that's one of the functions of a router. But if we want to allow certain people to come in, if I want to allow my friends to come in when I'm, like let's say I'm on vacation and somebody's got to water the plants, my cousin's got the keys, right? She can come into the house and she can turn off the alarm system and she can water the plants. Well, just as I give my cousin the keys to my house so she can come in, we set up these software ports in the router and in the firewall to say, if anything wants to come in and talk to port 8180, let it through and send it to this address on the local network. But while we're talking about the software ports, understand that you use these every day. When you go on the address line of Internet Explorer and type HTTP, you're saying, take me to port 80 on the ESPN.com server. And when the communication gets set up, then the ESPN.com is going to come back to you on a different port number, but you're going to be communicating to it on port 80. When you type HTTPS, you're saying take me to port 443. Now, there's two protocols. We're going to get back into that port forwarding thing and show you how it's done. But there's two of those protocols that we saw in the encapsulation that we want to talk about. They are TCP and UDP. The first one we're going to talk about is TCP. It's called Transmission Control Protocol. And this is what's called a connected communication. When you think TCP, think of a tennis game. I'm on one side of the net. I serve the ball to you. It goes over the net. You hit it back to me. This is the way that TCP works. If I'm a computer and I'm transmitting in TCP protocol to you, I'm going to transmit a data packet, and you're going to send me a receipt that tells me you got it. And then I'm going to send you another one. Now, some devices will send 2 packets and ask for 1 receipt. Some devices will send 4 packets and ask for 1 receipt. Okay? But receipts come back to the transmitter. And do you see that this guarantees reliable delivery? TCP is commonly used on the internet for document transmissions, email transmissions, and things like that. For the simple reason, think about it. When you open up an email, you want to see the whole email. You don't want to see 95% of it. You don't want to see some words missing. They might be important words, right? So we have TCP communication, and the reason that this is important to us as physical security professionals is that some of our IP-enabled video cameras and encoders often use a compression format called JPEG. We're going to talk about compression formats in great detail later, but right now, what I want you to understand about JPEG, or Joint Picture Experts Group, is that normally devices that use JPEG transmit the video in TCP. Now, a JPEG image that's transmitted from a camera is going to be a whole and complete picture. So if you're sending 10 frames a second through the network, you're sending 10 whole and complete pictures. JPEG is just like your snapshot digital camera. When you take pictures of the kids and then you store them on your computer, what does it store them as? .jpg files, right? Well, that's JPEG. And if we're doing video JPEG, or sometimes it's called MJPEG for motion JPEG, we're getting a stream of whole pictures. But we're transmitting in TCP, so we've got receipts going on, right? And other applications also use TCP, such as File Transfer Protocol, HTTP. These use TCP communications with the, in fact, when you think about the internet, right now on the internet, right this instant, whenever you're watching this, there are billions of data packets going through the internet. And of those billions of data packets, up to 50% or a little more of them are what? They're TCP receipts. TCP is commonly used over the internet, commonly used over the local networks. And here's the way TCP works. We send out a data packet, we get an acknowledgement sent back, and then the next data packet is transmitted, just like that tennis game I described. And here you see the addressing, the layer 4 addressing of a TCP header with our source address, our source port, destination port, sequence number, acknowledgement number. There's a whole lot going on in here to set up what is the TCP header. So it's a pretty big address package that has to go on each of the TCP packets, both the packets and the receipts. Now, TCP has flow control, so the receiving computer can let the transmitter know how big its buffer is and how much the buffer's filled up. So as it's sending back the receipts, it's also sending back, let's call it a report about how many packets it's received, how many more it can take, hey, speed up, hey, slow down. So we've got flow control when we have TCP communication. Another thing we get is congestion control. If we have too many unacknowledged segments or data packets, then the transmitter is going to slow down. It's going to throttle back and say, okay, well, I'm going to wait until I get some receipts here before I start sending more data. So we get congestion control as well. Now, the other type of protocol that's common that we need to be aware of is called UDP, or User Datagram Protocol. And in UDP uses what's called best effort. In a UDP transmission, the transmitter, let's say I'm a camera and I'm transmitting in UDP, I'm just sending you packets. It looks like this. Packet, packet, packet. No receipts. Now, I'm not going to wait for receipts. I don't really care that if you get the packets or not. I'm sending them, and I hope you get them. Now, UDP is commonly used for time-sensitive transmissions, like audio, like VoIP telephones, and like some video. The compression formats, higher-end compression formats that our manufacturers include in their video cameras and encoders will typically be of the MPEG-4 or now H.264, which is also called MPEG-10, a certain type of compression format. It is typically going to transmit in UDP. Now, do you see that if I have a camera that is transmitting TCP and I've got a similar camera transmitting in UDP, do you see which one is going to have less bandwidth requirement? It's going to be the one transmitting UDP because there are no receipts. Now, understand from the technician's perspective and from the alarm company perspective that you generally cannot choose on a particular product whether it transmits in UDP or TCP. What you can choose is the compression format that is used. because virtually all camera manufacturers include JPEG in their products because JPEG is a free technology. Anybody can use it. MPEG-4 and H.264 are licensed technologies. The manufacturer has to pay to put it into his or her product. So higher-end products will have MPEG-4 or H.264 now, and they're going to typically transmit in UDP. And it might be hard for you to find out exactly whether a device transmits in UDP or TCP unless you use a packet analyzer like Wireshark, which we're going to show you how to use later. And I've shown you a couple screens from it that shows you what the packets are and tells you whether things are UDP or TCP, as well as a lot of other information. And down at the bottom of the screen, you see that UDP is used for a domain name service, and a simple network management protocol and real-time protocol are some of the applications that use UDP. Now, one other thing I'll point out about UDP before we move on, and that is that particularly when we transmit over the internet, we are going to lose some packets. It happens. We shouldn't lose any packets in a properly configured local network. But over the internet, up to 5% of packet loss is considered normal. So we're transmitting audio signal. We're transmitting VoIP. It's a telephone call. It's going over the internet. Now, do you see that if a packet gets lost, and it's just going to be a little bit of information, just a little piece of the audio stream, right? It's not going to be, might not even be a whole word. A little piece of the audio stream is, it comes in late. It gets lost on the internet somewhere. It shows up 1 second later. Do you see that you don't want it now? Do you see that in terms of listening to the phone call, you've already moved past whatever that thing fell out of, so therefore you don't want it? So this is why UDP is used for these time-sensitive communications like audio, like VoIP, and it's also why UDP is not used typically for file transfers, emails, and other things that are of a document type nature. Because when we're transmitting a document, we want the whole thing. We don't want just a piece of it. And so you see the UDP function with no receipts, and here you see the UDP layer 3 address header that shows you there's a lot going on there as well in terms of setting up for UDP communication with our source address, our destination address, and the segments or datagrams from layer 4. Now this is the end of section 2 of this webinar series for the ESNT, Electronic Networking Technician Certification and Testing Program. This is provided to you by Slayton Solutions. If you want to invest and learn more, there are approved training and reference manuals, the Networking Security Systems Technician's Guide, which is on the left-hand side, and we have the Technician's Guide to Networking for Security Systems Enterprise Solutions on the right-hand side. These books are available. They're valuable information about networking, and they're available at our website, SlaytonSolutionsLTD.com. They're also available at ADI. Now, you can invest in the ESNT study guide, which may be where you got this, what you're looking at right now. But in your study guide, there is a section of questions that tests your knowledge about this particular section 2 and the information that we just covered. And the study guide also includes PDFs of the webinar sections, so you can print them out if you wish or review them. And the webinar's recorded, so you can review them too if you wish. And you can secure your future with the ESNT training and certification program. Thank you, and we'll be moving on to section 3.